This instructional video is designed to take advantage of what we understand of the first postulate and use that to create what we would call a superposition. The first postulate, written out in equation here, basically says that we can take the state of a system and specify it by making a linear combination of individual eigenfunctions. So the superposition takes that idea and says, well, we can fix the position of something. So if we suppose that we have a particle in a box and we wanted to fix the position of a particle in the middle of the box at L/2, then what we would need to do is figure out what the values of these individual coefficients are going to be. And we have to take into account what we already know about the amplitude of the wave function at that particular point. Now we can do that because we have wave functions that are relatively easy to look at and think about and understand. In fact, we know that if the value of n is even, the amplitude is always going to be 0 at the middle of the box. And we know that if it is odd, the amplitude will either be positive 1 or negative 1. So what may be useful is to actually try drawing out some of these. So we can start with n equals 1. Always good to start at the beginning. And see if we can come up with some kind of pattern. So if we're going from 0 to L, we have L/2 here in the middle. We know that we get 1/2 cycle of the sine wave. Then we can do n equals 2, going from 0 to L. And as predicted, we know we get 2 half cycles. And at L/2, this thing is 0. So we've got positive max amplitude here. You might suspect that when we get to side 3, that because we have 3 half cycles, 1, 2, 3, we see we have a negative amplitude. If we get over to side 4, and sketch that from 0 to L. We expect to have 4 half cycles or 2 full cycles of a sine wave. So we see we still have amplitude of 0. If we do number 5 from 0 to L, we're going to see 1, 2, 3, 4, 5 half cycles. Art's a little bit bad, but science. So for side 6, we'll again see that 0 pop in. And in this case, we've got 1, 2, 3, 4, 5, 6 half cycles. So in each case, just fix it up a little bit, we start seeing a pattern emerge. And so in that case, what we can do, I'll take the blue and mark the ones that we expect to have a coefficient that's going to be 0. So we expect to have a 0 coefficient here because this particular individual function contributes no amplitude. We see no contribution to the amplitude here, and we see no contribution to the amplitude here. So in all these cases, we expect to have a 0 in the sum because that does not contribute. Now, we can use the green to pick out the ones where we get a positive max amplitude, in which case we would expect that coefficient to be greater than 0. So we get a positive contribution for side 1. That is below, so that does not work. Number 5, we expect a positive contribution as well. And finally, if we look at the ones with a negative amplitude, we can multiply that by a negative number and get it to essentially flip and provide positive amplitude. So we would need those coefficients to actually be negative. Of the ones written, that's only side 3. So if we use what we know about the eigenfunctions that are pure on this side, then we can build up a superposition for a combined state, which is what we have on this side, that captures a lot of the features that we would want to have in our ideal system. And as a result, we can then write a rule that would generalize to all of our possible values, and by so doing, get an increasingly accurate result by adding in more and more terms.